Okay. Well, first I want to thank the organizers for inviting me to this very prestigious conference. So I'll be talking about work that I've done, various collaborators. There's Tristan Denon, there's Scott Davies, Volodya Smirnov, Sasha Smirnov, and then some work which will appear soon with Clifford Chung, Huan Hang Chi, Scott Davies, Lance Dixon, and Josh Noley. So the outline of the talk is, first I'll tell you about basic ideas and tools that we use. Then I'll make some comments about the status of supergravity divergences. And then specifically I'll show you a phenomena that gravity amplitudes have, which are called enhanced cancellations, enhanced ultraviolet cancellations. And then we'll switch gears a little bit to talk about the conformal anomaly and the role that it plays in ultraviolet divergences, and also the question of inequivalence or equivalence under duality transformations. And the key point of this talk is I'm going to show you that the ultraviolet properties of gravity amplitudes are quite subtle and interesting. Okay, so first, just a little bit about the basic tools that we use. So I'm not going to talk very much about these tools, but they're always in the background. So there's going to be a set of calculations that I'll be talking about. And underneath the calculations, there's some technology. The main technology we use is called generalized unitarity. And then something very powerful that helps us a lot is this duality between color and kinematics. Basically, it allows us to take gauge theory amplitudes and turn them into gravity amplitudes. It goes under the name of double copy construction. And then finally, at the end, we're actually interested in some what the actual divergences are. And for that, we need advanced loop integration technology, and that's adopted from QCD. And there's, of course, many other tools and advances, which I'm not going to discuss here. But some of that was discussed in the parallel sessions. So first, just a little bit about this duality between color and kinematics. So at loop level, this is a conjecture. It's not proven, but on the other hand, that doesn't stop us from using it because we have the unitarity method to check any conjectures. And the basic idea is that if you look at a loop diagram, then as we know that there's the color factors satisfy certain algebraic relations, namely the Jacobi relation. So what this diagram represents is just the Jacobi relation. Think of these as color diagrams. And what the conjecture states is that there exists a way of writing the amplitude such that the algebraic properties of the kinematic numerators is identical to the color factor algebraic properties. And by the kinematic numerator, I just mean what you get essentially from Feynman vertices. Okay? Now, let's suppose that this is true. Then, in fact, we can prove the following, that if you want to go from gauge theory to gravity, you just take the color factor and you replace it with a kinematic numerator. So it's like magic. And that gives you the gravity loop integrand. So the construction of gravity loop integrands is trivial if you can figure out how to do this. How to find a representation of the amplitude such that the kinematic numerators have the same algebraic properties as the color factors. And the theories I'll be talking about n equals 8 supergravity, n equals 5 supergravity, n equals 4 supergravity. And these are obtained from these constructions straight from Yang-Mills theory. So n equals 8 supergravity can be thought of as a direct product of two n equals 4 super Yang-Mills theories, and so on and so forth. I'll also be talking about pure gravity. The construction in that case is a bit more complicated because you need some projectors to remove some extra states. You can do some state counting, and you'll see that pure gravity, at least at loop level, can't be obtained in this very simple way. But nevertheless, by making use of projectors, it's straightforward to do that. And this idea has been applied in many places. So one of the new developments is the construction of non-trivial supergravity theories. So this has been discussed in many papers. Then if you're looking at string theory loop amplitudes, then it was Mafra, Schlatter, and Stieberger that make use of this, this duality between color and kinematics as guidance for the construction of string theory amplitudes. And actually something very neat is some recent applications to black hole solutions. What I'll be talking about is applications to ultraviolet properties of n equals 4 and n equals 5 supergravity. Okay, so I'm sure most people in this audience believe that the ultraviolet properties of gravity are very well understood, up to some minor details. For example, a minor detail might be the specific order, the specific loop order at which a divergence occurs. But in fact, the point of my talk is to show you that it's quite a lot more subtle and interesting than that, that it's full of surprises, very strange surprises. And the two surprises I'll be talking about, one of them is examples where you find no divergence when, in fact, it sure looks like the counter terms, the corresponding counter terms are valid. And then it turns out where you find the divergences, like in pure gravity or in pure n equals 4 supergravity, then when you look at the properties, they're not at all what you expect. And in fact, most of the talk will be about that. So in recent years, there's been quite a lot of work on the question of ultraviolet properties of supergravity theories. Many people, including Michael Green. In fact, there's quite a few approaches, which I won't get into here, but there's one approach that I like a lot, because once you strip away the technicalities of how it works, what they do is quite simple. The key idea is, in this formalism, so it's the first quantized formulation based on Berkowitz's pure spinors, the key point is that all the supersymmetry cancellations are exposed. So you can see exactly what's happening because of supersymmetry. And then what they do is they define some diagrams they call skeleton diagrams, and then they identify poorly behaved contributions. So they find that the diagrams are poorly behaved, and then the bottom line of what they say is there's going to be poor behavior in n equals 8 supergravity unless there exists new types of cancellations between diagrams that are not consequences of supersymmetry in any conventional sense. And the specific predictions they make is that n equals 8 supergravity should diverge at 7 loops in d equals 4, n equals 8 should diverge at 5 loops in d equals 24/5. Okay? Now, we've looked at this from our own viewpoint using unitarity, using scattering amplitudes and unitarity, but it's the same basic idea. So we use what are called maximal cuts. The basic idea is that you put all the legs on shell, so that would be a maximal cut. And then you identify a term that belongs only to this diagram. So you think of diagrams that are covariant, meaning only Feynman propagators, and then you can prove that all representations that are covariant necessarily have bad behavior. Certain terms appear. In fact, this is a term that you cannot move to any other diagram. And this diagram has poor behavior, let's say in n equals 4 supergravity at 3 loops. And this shouldn't surprise you, because remember from the double copy construction, you could take n equals 4 supergravity and turn it into pure Yang-Mills times n equals 4 super Yang-Mills. Okay. And of course, we reproduce exactly what Bjornson and Green found for n equals 8 supergravity. And we also had a look at n equals 4 supergravity, n equals 5 supergravity. And the predictions based on analyzing individual diagrams is that these theories should diverge. Let's say n equals 4 supergravity should diverge at 3 loops in d equals 4, n equals 5 at 4 loops in d equals 4. And this, in fact, these are where we made these bets. Like there's one with David Gross about 7 loops in d equals 4. Unfortunately, we never made any bets about this. But the basic idea is that we expose all the supersymmetry and we do the power counting. When you look at all the other groups, So they don't expose all the supersymmetry, so they make use of duality symmetries to make up for that. But everybody agrees this is where the divergence should be, based on symmetry. And if there is a cancellation beyond what's here, let's define that to be an enhanced cancellation. So that would be cancellations between diagrams. And in fact, we now have 3 examples like that. I'm not going to get into the details of how we did it, but it's based on those tools that I was telling you about. It's done explicitly. There's no doubt that what I'm telling you here is exactly how it works, because we just did the calculation. So it's not based on argument, but based on just checking directly. So D equals 4, N equals 4, pure supergravity is ultraviolet finite at 3 loops. N equals 5, supergravity, ultraviolet finite at 4 loops, contrary to the predictions. There's another one about half maximal supergravity in D equals 5 at 2 loops. And despite some effort to try to find standard types of explanations for this, in fact, there is no known standard explanation that actually works. And that was looked at by Bossard, Howe, and Stell, and also we had some fun with that. Now, one point about this that's actually important is this phenomena does not occur in non-abelian gauge theory. It's only in gravity. So if you're doing any kind of power counting based on how you think or how you know that gauge theory works and you apply it to gravity, you're going to run into some trouble. And in fact, from the way that these enhanced cancellations work and the fact that we've exposed all the supersymmetry, I think makes it very hard to find a standard symmetry explanation. Of course, I welcome people to try. Now, I'm sure people are going to ask me about the status of N equals 8 supergravity, so let me say a few words about that. N equals 8 supergravity, okay, we don't know how it works at 5 loops and beyond, but I think there's very good reason to believe that the same phenomena occurs starting at 5 loops. The enhanced cancellations start at 5 loops and go beyond. And also that it's very likely that N equals 8 supergravity is going to be finite at 7 loops, contrary to the predictions. And the reason why I say that is you just take the same arguments that were proven to be incorrect in N equals 4 supergravity and N equals 5 supergravity, and you apply it here. Obviously, you probably should not expect that those arguments are going to give you the correct answer. Now, to actually understand this properly, what we really need is a much better understanding of this duality between color and kinematics. And unfortunately, it's turned out that the construction of the 5-loop N equals 8 supergravity amplitude has been non-trivial, and that has to do with the fact that finding what are called these BCJ representations, so that's where the duality between color and kinematics holds, it's non-trivial. We need certainly a better understanding of the underlying theory. But we have made some recent progress, so we're going to write a paper soon that has to do with not N equals 8 supergravity, but the theory that underlies it, N equals 4 super Yang-Mills, that we found a representation that has excellent loop-by-loop power counting, and that I think is going to be an important step for constructing N equals 8 supergravity. So hopefully we'll be making more progress on this. Now, let me just tell you very briefly about 4-loop N equals 4 supergravity. So in that case, you find a divergence. And in fact, this is the first divergence anyone has found in a pure supergravity. And it has, there's a 1 over epsilon, so that's done in dimensional regularization. But the devil is always in the detail. So when you look in detail exactly what this kinematic factor is in front of the divergence, it has a very curious property. And that property is that it's present in sectors which would vanish if it was not for an anomaly in the duality symmetry. So that's not expected. There's some connection between this divergence and the anomaly. Now, it's a little bit unfortunate that we're at 4 loops, so everything is a little bit complicated. So you'd like to analyze a simpler case. Okay? There's only one other case where we know of in a pure gravity or pure supergravity where there's a divergence, and that's pure Einstein gravity, where we can analyze two loops. So what's going on here with the anomaly motivated us, one of the motivations at least, to have a look at pure Einstein gravity, re-examine that. And that's, of course, very well studied, and I think everyone here would believe there's no surprises to be found there. But let's talk about that. So in pure Einstein gravity, we know that it's one-loop finite. That was shown in the seminal work of Tufte and Beltman back in 1974. So the basic idea is that if you write down the valid counter terms, you can write down Ricci square. But Ricci square could be eliminated by a field redefinition. So that's out. And then the other possibility is Riemann square. But there's the Gauss-Bonnet theorem. So that tells you that the integral over this combination is just the Euler characteristic. The Euler characteristic, if you're in an asymptotically flat space, is just 0. So this is an evanescent operator. By an evanescent operator, I mean it's just 0 in d equals 4. Outside of d equals 4, it's non-zero. Okay, and that's actually going to play an important role in what I'll be talking about, because we're going to be working in dimensional regularization, and the issue of the proper treatment of the Gauss-Bonnet term is non-trivial. And that was noticed back in 1980 by Capper and Kimber. But this issue only becomes important beyond one loop. Now, you could also consider a space where there's non-trivial topology, and then what you find is there's a divergence. It's proportional to the Gauss-Bonnet term. By the way, this one-loop finiteness, that's an example of an enhanced cancellation, although in this case, you could say it's kind of trivial because we understand exactly why it happens. It's just the Gauss-Bonnet theorem. Okay? In other cases, it's not understood exactly why it happens. Now, this divergence, the one-loop divergence of gravity, this Gauss-Bonnet term, it's exactly just the conformal anomaly. So when you look at the trace of the energy momentum tensor, you'll see that you find exactly the same numbers appearing in the divergence as appear in the trace anomaly. The trace anomaly, we could call it the conformal anomaly, Weil anomaly. It's those words are used in the literature. And this shows you the different contributions from different kinds of matter that you put in into the loop. Now, there's something very strange about the conformal anomaly. And this was noticed by Duff and Van Evenhuizen. So what they noticed is that the contribution to the trace anomaly of a scalar and a two-form are different. In fact, they differ by a factor of 91. On the other hand, you know that a scalar is dual to an antisymmetric tensor in d equals 4. So that seems very strange. How could there be a factor of 91 difference? Maybe you'd think it'd be whatever the difference is, it's suppressed by order epsilon. But in fact, there's when you do your order epsilon counting, you have to account for the fact this is the Gauss-Bonnet term, so there's like a hidden order epsilon. In fact, this is there's no doubt this is correct. The antisymmetric tensor contributes 91 times as much as a pseudoscalar. And then the three-form, that guy is a very strange beast. That has no degrees of freedom. No degrees of freedom, yet it contributes to the conformal anomaly. That's very strange. So Duff and Van Evenhuizen wrote a paper with the title Quantum Inequivalence Under Duality Transformations. And then 4 months later, Warren Siegel wrote another paper where he changed the title by getting rid of the word in, and he made it quantum equivalence. Essentially, he was arguing that there's gauge dependence in this answer. I can't say I really understand Warren's paper, and also it's not clear to me that what he was saying is compatible with what we're saying. But anyway, he's definitely in the camp of quantum equivalence, that this is just some artifact of some kind. And other people also commented on this. There was Fratkin and Setlin. There was a very detailed analysis for the one-loop effective action, and they came down firmly on the side of quantum equivalence. Now, something important that you always have to ask about any claim of quantum inequivalence is the issue of what it actually means. And you have to be a little bit careful with that. You have to look at a physical quantity. And we're going to have a look at it, and we're going to look at cross-sections. Okay. No, I think you're wrong. Yeah? When do we start? Huh? Oh, okay. Okay, got to move. Okay. Now, when you look at, we're going to look at the scattering amplitudes. And when you have a look at the scattering amplitudes, you start finding some very strange phenomena. So this divergence, the divergence, the two-loop divergence, which is given, this is given by Garoff and Sagnati. When you have a look at this in a little bit more detail, you find that it contributes to this identical helicity amplitude. And immediately that's very strange, because when you look at the identical helicity amplitude, you discover that in d equals 4, if you put the inner legs in d equals 4, the amplitude just vanishes. And in fact, Bardeen and Kangemi, they pointed out that the non-vanishing of these identical helicity amplitudes is connected to an anomaly in the self-dual sector. They were talking about self-dual Yang-Mills, but through the double copy, it's really the same as talking about gravity. Okay. So we went ahead and we had a look at this. We did the calculation using modern technology. When you can add up the diagrams, in fact, you don't find the Garoff and Sagnati result. You find a very different number. Actually, these prime numbers, product of these prime numbers, 47 times 73 is what we found, not the 209 of Garoff and Sagnati. But Garoff and Sagnati, they subtracted subdivergences. They did that integral by integral. For various technical reasons, they had to do that in order to get a sensible answer. Now, the way we do it is we have the entire amplitude. So you might ask about the subdivergences. What subdivergences are we talking about? Because there are no one-loop divergences, right? Well, not exactly. If you have a look at, if you have a look at, let's say, an amplitude, so this would be where you've collected all the diagrams together, and you're looking at the Gauss-Bonnet subdivergence. If you put these legs in d equals 4, indeed, there are no subdivergences. But we're doing dimensional regularization. In dimensional regularization, d is not equal to 4. Then, in fact, there is a subdivergence. So we have this very weird situation that there are no one-loop divergences, but indeed there are one-loop subdivergences. And if you look at the explicit integrals, that's exactly how it behaves. So we need to subtract the subdivergences. So that's what we did. So here's the Gauss-Bonnet. That's a one-loop. That's an insertion of the Gauss-Bonnet into one loop, and this is two insertions of Gauss-Bonnet into tree. Those are the counterterm contributions. So you have to do the calculation. There's some technology that goes into it. And then you get some numbers, and you add up the numbers, and there it is. We have Garoff and Sagnati. But notice the key point. The anomaly enters. Right? And this part here, it's not entirely the conformal anomaly, but it does have this anomaly-like behavior that if you put these legs, the inner legs in d equals 4, the amplitude just vanishes. Now, what does the divergence mean? Well, there's a good way to understand the meaning of the divergence by thinking about three forms, because three forms don't contain any dynamical degrees of freedom. So on the one hand, you might expect that there wouldn't be any change because it doesn't have any degrees of freedom. And maybe you think it's and there's no dynamical degrees of them into a counter term. So in fact, you could think of this three form as a Cheshire cat field. It kind of disappears. It has no physical effect. And in fact, the same type of idea, it happens comparing this GD theory to the GA theory. So the bottom line is our results are consistent with quantum equivalence under duality. And this is second to last slide. Okay. So So I just told you that the divergences, they don't really mean anything directly because it makes a difference exactly how you complete the theory and what your field representation is. But instead, we should be looking at the renormalization scale. So when you look at the renormalization scale, you find actually something very nice. For all the theories we looked at, so a single antisymmetric tensor field or dilaton, or changing three forms, or adding one three form to the 4 graviton amplitude, what you find is the renormalization scale dependence, the log m square, it has a very nice number. The number of states divided by 8. In fact, there's a fermion minus sign if you look at a fermionic theory. So in fact, this would be 0, which is nice because the 4 graviton amplitude is finite in a supersymmetric theory. So the divergences differ under the duality, but the scaling behavior is identical. That may sound very strange, but remember, we're dealing with these evanescent operators, so things don't work the way you think they do. So first thing, notice the simplicity of the number. So this is the appropriate number. There's no weird prime numbers. This coefficient, log m square, it's a better measure of the divergence properties, and it's the proper quantity to study. In fact, with that n equals 4 supergravity theory at 4 loops, the divergence we calculated, in fact, matches the log m squared. So in that case, that divergence was meaningful. If we made duality transformations, I'm sure you'd get different divergences. And then maybe one more comment is by looking at this discrepancy between the scaling behavior and the divergence, I think that could offer some insight in how to do ultraviolet completions. Okay, so the final summary is I showed you examples of enhanced cancellations. The UV is better than expected based on standard symmetry considerations. We reproduced the Gaurav and Sanyati result, but the surprise is the way the conformal anomaly enters. In fact, the entire answer, it looks like it has an anomaly behavior. It's like a 0 over 0 behavior, and it's connected to Bardeen and Kangemi's observations on anomalies in self-dual field theory. And then I showed you that these ultraviolet divergences, they depend on the duality transformations or additions of non-dynamical 3 forms. It's much better to be looking at the renormalization scale instead of the divergences. And we came down on the side of quantum equivalence under duality. The divergences might change, but the logarithms are identical. Okay, so the final comments are that the question of the ultraviolet properties of supergravity theories, after all these years of study, it's still an open problem. And most certainly, the question of the ultraviolet properties of gravity theories, it's full of subtleties and interesting twists. And I think that as we do further studies, we should expect many more surprises when we use these modern tools. Okay, thank you.
Sorry, you at the beginning you offered some formulas for conformal anomalies, but it's not clear to me that the theories you were discussing were actually conformally invariant. To begin with, there's pure gravity, which isn't conformally invariant, so I'm not sure what's meant by the conformal anomaly.
That's right. So I'm not the person who named it that, but you're absolutely right. There is no conformal symmetry not in the Lagrangian, but in the equations of motion. There's a scaling symmetry.
But not a local conformal symmetry.
That's correct. Not a local conformal symmetry. Anyway, it's just a terminology. I take no responsibility for naming it that.
But I want to point out that the same is true for the 3-form theory.
Right.
When you have an anomaly proportional to the Euler characteristic, to make sense of it, you have to be on a manifold where there are these 0 modes. And then to make sense of the path integral, you need Dirac quantization. And Dirac quantization isn't conformally invariant. So if there's a contradiction in the literature, it's probably because the theory isn't conformally invariant.
Yeah, that's fine. But at the end of the day, the right thing I think to do is actually delete the word anomaly. But what remains is anomaly-like behavior in the sense that what we're finding has to do with evanescent operators. It has to do with these 0 over zeros.
Yes. Okay. Can you go back 1 or 2 pages and show us where the difference came in between the divergence and the logarithm?
Yes.
Okay.
So
there was
yeah, this would not happen in a normal theory like QCD.
But, sorry, when you have log minus s, what's the denominator of that?
Oh, it's actually, that's in fact how you count the log m's, because there's a mismatch in dimensions.
Yes.
So the log m's, you really could divide by log m by the renormalization scale.
Okay. When you do dimensional regularization, though, that logarithm and the m didn't come in because of the 1 over epsilon. That's all I was trying to ask.
Yeah, so there's a mismatch. I mean, your observation is exactly right. So let's say we think about one loop QCD, the divergence is tied to the log m. Here it's not.
Okay, thanks.